Okay, the previous section I was referring a lot to significant digits and uncertainty because when we're working with measurements, it's different from working with a number. A number is a number, but a measurement has three parts. It has the value of the number, the units that the measurement is, and the uncertainty of a measurement. Any measurement you take has some uncertainty. And the way you report the measurement is how you let people know how certain you are of your measurement. If you report 52.7 milliliters, that last digit that you report is where the uncertainty is. So it means that you were able to measure within 0.1 milliliter. The 7 could have been a 6 or it could have been an 8. So that's what you're implying. Okay, let's contrast 52 milliliters with 52.0 milliliters. Instead of using 52.7, let's use 52.0 because 52.0 and 52 numerically are the same thing. Your calculator will treat them the same. But if you report something as 52, your 2 is uncertain. So it could be a 1, it could be a 3. It's 52 milliliters plus or minus 1 milliliter. So you're saying it's somewhere between 51 and 53 milliliters. If instead you report 52.0 milliliters, then the 0 is what's uncertain. So it's plus or minus 0.1 milliliter, not plus or minus 1 milliliter. It's plus or minus 0.1 milliliter. So it's a much shorter range between 51.9 and 52.1 milliliter. It's not all the way at 51 or 53. So the way you report a number matters. Okay, so what if we had a number that was 52.756 milliliters? Well, this is quite an impressive instrument because we are saying that the 6 is the uncertain number. So it means plus or minus 0.001 milliliters. Not very much uncertainty or variation at all. So we're saying that our measurement, we are confident that it's somewhere between 52.755 and 52.757 milliliters. So that's some pretty good confidence in our measurement. You can have exact numbers, just not for a measurement. So let's go over when we can have numbers that are truly exact. Some people think that if it's 52.0 that it's exactly 52, or if you just put 52 then you mean exactly 52, but that's not what we mean by exact. Exact number means there's no uncertainty. So if you count something, if things come in discrete items like a beaker, and you count that there are 4 beakers on the lab bench, it means that there are exactly 4 beakers. Not somewhere between 3 and 5 or somewhere between 3.99 and 4.01. It means exactly 4. We also have the because I said so rule. For instance, a unit that is defined as exactly a certain number of another unit, then it is, by definition, exactly that amount. So the metric system is a good example of that. The definition of a kilogram is that it's exactly 1,000 grams. There are some other ones. For instance, an inch is defined as exactly 2.54 centimeters. So if we do come across a relationship that is exact, I will specify that so that you know that it's a defined relationship. All right, let's go through these and see if we can figure out which things are uncertain or exact. Remember that uncertain number is anything that's measured or anything that's based on a measurement. So this first one, measuring a stack of paper that has a ream of sheets in it, is a measured value. So this is uncertain. The ruler that we used has an uncertainty of plus or minus 0.01 centimeter. This could be 4.76 centimeters. There is a little bit of uncertainty there. This is part of the metric system, centi and milli, metric prefixes. So this is exact. So just because we use this exact relationship to convert centimeters to millimeters, we kind of use this relationship. it doesn't mean that we've become any more certain. So just like this 5 could have been a 6, now that we've converted it to millimeters, the 5 still could be a 6. We're a little bit uncertain there. Okay, well this is counted or defined. So a ream has 500 sheets, not 499.7 sheets. So this is exact. And then when we divide this uncertain measurement by an exact number, we still get an uncertain result. Because the uncertainty in our measurement gives us some uncertainty as far as how thick each piece of paper is. Okay, this part is pretty helpful for lab. You might have already seen this in lab if you went to lab first before watching this. When you are recording a measurement that's taken by a digital instrument, please use all the digits that are given by the digital display. If you put something on the balance and it says 42.800 grams, some students are tempted to just write down 42.8, but remember 42.8 is different from 42.800. The uncertainty of this balance is 3 past the decimal. If it were not, then the balance would be manufactured to have fewer digits in its display. So we're trusting the people who made the digital display to know what their uncertainty is. Something like a ruler or a graduated cylinder has marks on it, and we are going to estimate one place value past the line markings. So if the line markings are in the hundreds place, we are going to go one place value to the right, and the tens place is what we're going to record to. So for example, if we were measuring a piece of paper or something, and we could see that it's between 400 and 500, we can estimate that it's 450, even though there's not a line for 450. That 5 is uncertain because we're estimating it. So if the lines are every 10, we're going to go one place value to the right and record to the ones. Here's a ruler with markings every 10 millimeters, 440, 450, 460 millimeters. And so we are estimating to the ones place. There's not a line for 452. We had to estimate that too. Somebody could have said it was 453, but we're estimating a little bit further. All right, let's take a look at this ruler that's marked every 1 millimeter. So for this orange string, we can see that it's between 452 and 453. We're going to record it to the 0.1 millimeter. Again, one place value past where the markings are. So instead of just saying that it's 452, we're estimating that it's 452.3. It's about a third of the way past. So that 3 is uncertain. We're not uncertain about the 452. There's a line right there for the 452. We're uncertain about the 3. That's why we're estimating an additional digit, because that is the uncertain digit. The digit we don't have to estimate is not uncertain. We're going one past that. So let's take a look at what happens if we have like these red strings that are right on the line. Okay, so this red string, we wouldn't want to call it 452.3 because it's not past the line for 452. It's right on the line. So this orange string we would call 452.3 millimeters, showing that we're uncertain about the 3. This red one we're going to call 452.0. We are supposed to be estimating to the 0.1 millimeter, so we need something 1 past the decimal. And since it's on the line, we're estimating a 0 as what that something should be. We could go back a little bit. This purple one we estimated as 452 millimeters. We're estimating the ones place, so we're uncertain about the ones place. This one is on the line, so we have to call it 450 millimeters. This one's a little bit trickier because we want to show that it's plus or minus 1 millimeter. Just like this purple string, we measured it with the same ruler. They're both plus or minus 1 millimeter. As opposed to this green string, which is 450 plus or minus 10 millimeters. We want to show that this is 450 plus or minus 1 millimeter. And so to do that, we put a decimal here because that turns the 0 into a significant digit. We'll get to that in a little bit. But this 450 with a decimal has 3 significant digits, and the 0 is the last significant digit. This 450 without a decimal has 2 significant digits, and the 5 is the last significant digit. Okay, and finally, if we have a ruler, or if we have some lines every 0.1 millimeter, then we are going to go an additional space and record it to the 0.01 millimeter. Let's practice that with this drawing over here. If you'll notice, these 4 measurements are really taken with 2 different rulers. These are both taken with a ruler marked every 1 centimeter. These are both taken with a ruler marked every 0.1 centimeter. The difference between these 2 measurements, we are saying that this one is between the lines and the second one is on the line. So I wanted you to practice both, taking a measurement that falls between the lines and taking a measurement that falls on the line. So let's remember that we want to go 1 decimal place past, or 1 place value past where the markings are. So for the 1 centimeter ruler, we want to record to the 0.1 centimeter. For the 0.1 centimeter ruler, we want to record to the 0.01 centimeter. So here we would record it as 33.6 centimeter. The 6 is uncertain. Maybe you would put 33.7 centimeters. That's okay. And this one we would record as 34.0 centimeters because the 0 is what's uncertain. The 4 is not uncertain. So we need to go to the 0.1 centimeters. This first string is between 16.7 and 16.8. I eyeballed it about halfway in between, so I put 16.75 centimeters. If someone put 16.76 centimeters or 16.74 centimeters, that would be true as well. This one is on the line for 16.8 centimeters, but we're not uncertain about the 8. We're uncertain about the next place value. So we need to record this as 16.80 centimeters. So just notice that the 2 measurements taken with the same ruler are exhibiting the same amount of uncertainty. Significant digits are kind of a shortcut for showing which place value has your uncertainty, because we mentioned that the last significant digit that you show is where your uncertainty is. So the first thing we have to do is know how to figure out how many significant digits we have in a measurement, which digits are significant. And it's pretty easy for non-zero digits. So the non-zero digits are significant. It's pretty easy to show that this 6 is saying something. If you didn't know what it was, why would you write a 6 instead of just a 3 or a 2 or a 0? So anything that's non-zero is significant. Zeros can have more than one function in a number. Our example before had 450 millimeters as one of the measurements to show that it wasn't 451 millimeters. And then we had another measurement that was uncertain to the tens place, and we just had the 0 here, not to show that it was 450 instead of 451, but to show that it was 450 rather than 45. If we drop this 0, we're going to change the number drastically. So zeros can both hold the place value, that this 5 is a 50, not just a 5, or it can actually express data. These rules help us determine when a 0 is expressing data and when it is just holding the place value of the number. So the position of these zeros, we're going to talk about the left, in between, or on the right. And those positions are relative to the non-zero digits. Zeros to the left of the non-zero digits are never significant. In between the non-zero digits, those zeros are always going to be significant. And to the right of the non-zero digits depends. It depends on whether the number has a decimal or not. Some people get confused and think that we're talking about zeros to the left or right of a decimal. We're not. We're talking about zeros to the right of non-zero digits, and those are the zeros that depend on whether the number has a decimal. So for this number here, these zeros are to the left of the non-zero digits, so they are not significant. This number has 2 significant digits. This 0 is to the right of the non-zero digits, and there's no decimal in the number. So that is not significant. We have 3 significant digits in that number. These zeros are to the right of the non-zero digits. They're all to the right of the non-zero digits. Some of them are to the left, or one of them is to the left of the decimal, but they are all to the right of the non-zero digits. And there is a decimal in the number. So these are all significant. We have 6 significant digits in this measurement. This 0 is in between. It's always significant. This 0 is to the right. It depends on the decimal. There is no decimal, so this one is not significant. We have 3 significant digits in this number. These are in between the non-zero digits, no matter the position of the decimal. So they are always significant. And these 3 are to the right of the non-zero digits. So they depend on the decimal. There's no decimal, so they are not significant. All right, just a quick reminder when you're rounding numbers. If you want to get rid of digits to the right of the decimal, you have to chop them off. You should definitely chop them off. If you want to get rid of digits to the left of the decimal, you need to use placeholder zeros. I have this little example to help us remember. So if you need to get paid $100 and you round it off, or somebody rounds it off for you, if they put 100, that's still okay. Chopping off the zeros to the right of the decimal is fine. If they started chopping off the zeros to the left of the decimal, you would be a little bit upset to see that on your paycheck. So let's go ahead and round these. We want 3 significant digits. We count off 1, 2, 3. We take a look at the next one. The next one is large, so we're going to bump up the 8 to a 9, and we're going to make this 12.9 grams. This one over here, 1, 2, 3. This next one is large. When we bump up 4.99, it becomes 5.00 milliliters. This one over here, 1, 2, 3. The 3 is small, so we'll keep the 6. But we have to have a placeholder 0. 1,163.7 milliliters is close to 1,160 milliliters. It is not close to 116 milliliters. Then this one over here, 6, 7, and 4. The 4 is going to change to a 5 because the 8 is large. So this is close to 67,500 centimeters. Some people do make the mistake of keeping all the places and just changing the numbers to zeros. That's not what we want to do, because this is telling us that we know to within 0.1 centimeters. What we're really trying to say is that we only know to the closest 100 centimeters. That's the reason why we're rounding it off. So this, even though it has the same value, makes us look more certain than we are. Sometimes instead of the number of significant digits, we want to round something based on the place value. So if we know that we know something to the hundredths place or 2 past the decimal, then we're going to round it based on that. So this would become 8.46 liters, and this would become 438.99 millimeters. This one we want to round to the hundreds place, so plus or minus 100. So this would be 12,100 milliliters. You could put the comma or not. That's just to make numbers easier to read. That does not affect the significant digits. This one we have the hundreds place here. So this is 5,700 millimeters. When you do calculations with uncertain numbers, the uncertainty carries through your calculations. So we can say that a chain is only as strong as its weakest link. So if you are doing a bunch of calculations on measurements, you're only going to be as certain of your answer as you are of your least certain measurement that's going into that calculation. For multiplication and division, we can figure out the least certain measurement based on the number of digits. And for addition and subtraction, we are figuring that out based on the place value. So here we have a number with 3 significant digits multiplied by a number with 2 significant digits. These are all multiplication and division. We're going to go with the number of digits. So our answer has to be rounded to 2 significant digits. My calculator gives me 30.52, but I know I just want 2 significant digits. So I'm going to round this to 31. And then I'm also going to put the units. The milliliters cancel and I have grams. Here we have a number with 4 significant digits divided by a number with 3 significant digits. My calculator tells me 92.52217, a bunch of digits. But I only want 3 significant digits because of this lower value here. So this is going to be 92.5. The grams have canceled, so I am putting this milliliters. Here we have 5 significant digits in the numerator and only 1 significant digit in the denominator. My calculator gives me a lot of digits. I can only keep 1. So this should be reported as 0.1 grams per milliliter. The video for section 1.4 was mentioning that if you are going to use these numbers in future calculations, sometimes it's good to keep some extra digits either in your calculator using the memory button, or you can note it on your paper or your notes. Carry through these extra digits and then round it off at the very end if you have a several step calculation. So for example, if you had 30.52 grams and you were going to do another calculation on it, you could write that as 30.52 with these being small, or you could write it as 30.52, underlining the 0 to show that the 0 is the last significant digit. But if 30.52 or any of these numbers is the final value being reported, then that's why we're rounding this off. So if it were the final answer, we would round it off to 31 grams. If we are carrying it through future calculations, we might want to keep a few extra digits and round off at the end. Okay, let's go back to this last example. We have something with 4 significant digits being multiplied by something with 5 significant digits. So we want our answer to have 4 significant digits. When I do this on my calculator, it just tells me 2, which only has 1 significant digit. To show that I am more certain than that, I can add some zeros. I have not changed the value, I still have 2, but now I'm showing that I'm much more certain of the 2. And then of course the units I need to take care of, they are centimeters squared. For addition and subtraction, remember this is based on the place value. A lot of times it's good to line up in a vertical fashion. So the way that your math problems used to look in 3rd grade. Just line it up and down. And then even though your calculator only gives you 2 digits, 66, you can tell that you know these values to 3 past the decimal, plus or minus 0.001 grams. So we can really express that in the answer as well. We can add some more digits to make this go 3 past the decimal also. When I line this next one up, I can see that this measurement, 7,300 meters, is known plus or minus 100. 5,160 meters is known plus or minus 10. So I have uncertainty in both the hundreds and the tens place. I can't have that. The uncertain digit is supposed to be the last digit that I report. So if the 4 is uncertain, that should be the last digit I report. I shouldn't be reporting other digits after that. If it's plus or minus 100, the 60 really doesn't mean very much. Although the 6 being large can help us because this is closer to 12,500 than it is to 12,400. So we will use that to bump it up. We'll go ahead and make this 12,500 meters. All right, here we've lined this up again. We have 850, which the way it's written implies plus or minus 10. Then we have 1.33 milliliters, which is plus or minus 0.01 milliliter. So our answer has uncertainty both in the tens place and in the hundredths place, 2 past the decimal. So if we are not sure of this digit, plus or minus 10 milliliters, then all these other digits become kind of meaningless. So we're going to have to round it to the tens place. which gives us an answer of 850 milliliters. We bump it up because the 8 is pretty big. So some people are a little bit confused by this because we end up with the same thing that we started out with. But if you think about it, if you don't know if this 850 milliliters is 860 milliliters or 840 milliliters, if you know this measurement plus or minus 10 milliliters, then 1.33 milliliters really doesn't make that much of a difference in that value. Okay, so this first value we know pretty well. We know it 5 past the decimal. This one we know 2 past the decimal. That gives us uncertainty at 2 different spots in our answer. And again, we're going to pick the larger place value, which is more to the left. So we are going to make this 7.85 centimeters. We bump it up because the 5 is big, so we bump the 4 up to a 5. Let's do a quick review of scientific notation and then also show you how useful it can be with significant digits. So scientific notation has a coefficient and an exponent, a power of 10. 10 to the 5th is 10 multiplied by itself 5 times, which makes 100,000. If you have a negative exponent, that is the same as 1 over the positive exponent. So 10 to the negative 3 is 1 over 10 to the 3, which is 1 over 1,000, which is 0.001. 10 to the 4 is 10,000. 10 to the 2 is 100. 10 to the negative 1 is the same as 1 over 10 to the 1, which is the same as 1 over 10, which is 1/10 or 0.1. And then anything raised to the 0 power, remember, is 1. So 10 to the 0 is not 0, it is 1. One way that a lot of students remember how to convert a scientific notation into a regular number or a standard notation number is that if it's a positive exponent, remember these numbers were very large. Negative exponents made numbers that were smaller than 1, numbers that are small. So we are going to make 4.7 bigger by 6 orders of magnitude. So 1, 2, 3, 4, 5, 6. So we have 4,700,000. 5.73 needs to be made smaller by 2 orders of magnitude. So it's 0.0573. You can write the 0 in front if you want. Some people don't want to. So 3.011 gets bigger by 3 orders of magnitude, making 3,011. And 2.9 gets smaller by 5 orders of magnitude, making 0.000029. When you multiply 2 things together, their exponents add. When you divide, remember that 1 over 10 to the 4 is the same as 10 to the negative 4. So we are going to have a 2 and a negative 4 added together, or 2 minus 4. So that would be 10 to the negative 2. For this exponent, we're having negative 7 minus a negative 3, or negative 7 plus 3. So this is 10 to the negative 4. For this, they add together. This is also 10 to the negative 4. This one is 10 to the 5. 10 to the 2 minus, 2 minus negative 3 is 5. 10 to the 5 times 10 to the 0. 5 plus 0 is 5, so we have 10 to the 5. This is kind of an interesting way to prove that 10 to the 0 does equal 1, as we said before, because if something multiplied by a number gives that same number, then it has to be 1. If 10 to the 0 equaled 0, then the answer to this problem would be 0, but it's not, it's 10 to the 5. So let's practice converting numbers from standard into scientific notation. Scientific notation has to have the decimal in between the first 2 digits, so we have to make this 6.54. Since we made it 2 orders of magnitude smaller, we counteract that by having something that is 2 orders of magnitude bigger. You can always double check by going the other way. 6.54 times 10 to the 2 is 6.54 times 100, which does equal 654. Let's do this one next. Again, we have to have the decimal in between the first two non-digit numbers. We made it 100 times bigger when we did that, so we have to counteract that by making it 100 times smaller. Sometimes when we do mental math on some scientific notation, we end up with an exponent, but then the term is not correct because we don't have the decimal in between the two digits it's supposed to be in between. So 0.0022 is actually 2.2 times 10 to the negative 3. If we keep the 10 to the 5, then we end up with 2.2 times 10 to the 2. And if you multiply 0.0022 times 10 to the 5, or if you multiply 2.2 times 10 to the 2, you end up with 220. So you can double check yourself by seeing that both of these values are 220. Over here, we can't have 4,318 in our scientific notation. This is really 4.318 times 10 to the 3. Then we keep the 10 to the 2. So overall, this is 4.318 times 10 to the 5. And you can double check yourself. Both of these, if you convert them to a more standard number, equal 431,800 or 431,800. It is important to know how to use your calculator to do scientific notation, but we can practice with some mental math on scientific notation as well. Let's go ahead and group these numbers together. 2.5 times 4 is 10. 10 to the 3 times 10 to the negative 1 is 10 to the 2. We have to change this into correct scientific notation, so we'll make this 1.0 times 10 to the 2. I probably should have put a decimal after this 10 to show that it has two significant digits. All right, 5.0 times 7.0 is 35. 10 to the negative 4 times 10 to the negative 2 is 10 to the negative 6. 35 times 10 to the negative 6 should really be written 3.5 times 10 to the negative 5, because we have 3.5 times 10 to the 1 times 10 to the negative 6. All right, 2.0 over 8.0 is 1/4. 2/8 is the same as 1/4, so this is actually 0.25. 10 to the negative 3 over 10 to the negative 5 is 10 to the 2. So this would be equal to 2.5 times 10 to the 1. 3 over 6 is the same as 1/2, 0.50. I'll keep my two significant digits. 10 to the 4 over 10 to the 6 is 10 to the negative 2. So this should really be written 5.0 times 10 to the negative 3. Let's take a look at something cool about scientific notation regarding significant digits. The important thing is that in scientific notation, the power of 10 tells where the decimal belongs. So you don't need placeholder zeros in a scientific notation number. So here we have 25,000 with some placeholder zeros to show that it's not 25 or 2.5 or 250. That's what these zeros are doing. But if we have this number with only two significant digits, then these are the only numbers we have to keep when we put it in scientific notation. We would write it as 2.5. We wouldn't use these zeros anymore. We would just put that as 10 to the 4. So this is how we would show this with two significant digits. What if we wanted to show that this was actually 25,000 plus or minus 1 with 5 significant digits? Well, we could do that also. We'll just keep all the digits that we really want. So this time we really want the zeros. They're not just placeholders. They're showing that these are equal to 0. They're not 1s, they're not 9s. So we can keep this 5 significant digits. So however many digits are in this first term, 5 digits, that's how many significant digits there are, because anything we kept is significant. So here this is just showing 2 significant digits. If we wanted to show 6 significant digits, we could do that too. Here we have 6 significant digits. We keep all 4 of the zeros. What's really interesting is if we want to show something that's not very easy to show in regular notation. What if we wanted to show 25,000 plus or minus 100? We want to show that the uncertainty is here. We can't show that by putting a decimal here because that would change the number to 250. We can't put the decimal here because then we'd have 5 significant digits. We can do something like underlining, or we could do something like writing it with a little subscript. Write the first 0 large and the other 2 zeros as a smaller subscript to show that there are 3 significant digits. But the easiest way is probably to use scientific notation. We can just write this as 2.50 times 10 to the 4, and that shows that we have 3 significant digits. Since this is the number of digits we kept in the scientific notation, that's how many significant digits we have. All right, so let's convert these to scientific notation, keeping the right amount of significant digits. This first one has 4 significant digits, so we need to keep all 4. This one has 3 significant digits. We're going to lose these leading zeros when we convert it. So our scientific notation has just 3 significant digits. All of these zeros are significant, so we want to keep all of them. I'll put that we have 5 significant digits here. For this one, we have 1 significant digit. These trailing zeros are not significant. We're not going to keep them. This one has 3 significant digits, so we'll keep all of those. And this one has 3 significant digits. We're going to keep the trailing 0. That one is significant. These 4 are going to go away. So we have 3 significant digits in our scientific notation. I already have another video that goes over this page and some more on standard deviation, so I am going to post those instead and stop this lecture at this point.